All right, guys. Well, we'll start. I don't know where everyone else is, but we'll get started. So if you recall last time, we were trying to do these line integrals on these vector fields, and we were looking at the fundamental theorem of line integrals that said that if our vector field was a conservative vector field, in other words, it was the gradient of some scalar function little f, that we could apply the fundamental theorem to it. So the last example in this section says that I have not shown you what it actually requires for a vector field in three-dimensional space to be conservative, but we can still use that idea of partial integration to try and find a potential function if it actually exists. So the last example will give you a vector function in three-dimensional space and ask to find its potential function. So that's what I'll do. So we're given a vector field. We can write that f of x, y, z if you'd like. It is the vector 2xz plus y squared, 2xy, x squared plus 3z squared. And I'm trying to find a little f, a scalar function, such that the gradient of that is equal to that vector field. That's what I'm trying to do. Find a little f such that the gradient of that little f is the capital F vector field. So the way we did it last time, do you remember what we did? How we started this? Partial integration. So what would be my first step here for this partial integration? Okay, so using that piece of information right there, I know that that's the partial of f with respect to x. This one should be the partial of f with respect to y. This one should be the partial of f with respect to z. If it does come from a potential function, right, if it has a potential function, then each of the components should be partial f with respect to x, y, and z respectively. So the way I started last time is I started with this first one. I said, all right, partial of f with respect to x needs to be equal to 2xz plus y squared. And then we integrated that with respect to x. So when I integrate the left side with respect to x, I'm going to get something. But then on the right side, what is the antiderivative of 2xz plus y squared with respect to x? X squared z plus y squared x, and then plus, here's the thing. It's a constant, right? But because this comes from a little f that has x, y, and z in it, anything that had just just y or just z, the derivative of that would have been 0. So this constant, instead of it just being a constant, it can actually be a function of y or possibly z. So I will just call it a function of y and z. So if what's out here has y's and z's in it only, the derivative of it would have been 0, right? Does that make sense? Yes? Okay. All right. Yeah, I'm not going to put dx in. Last class I did put dx in there, but we'll just say, look, since we know it's with respect to x, we're going backwards, we know it's with respect to x. So now the left side just becomes f, little f. We know little f, right? That's what this is. Must be x squared z plus y squared x plus some function g of just y and z. Now what we did was we said, all right, well, I know now this piece, 2xy, must be the partial of f with respect to y. So I'm going to come down here and I'm going to take the partial of f with respect to y on both sides. So what is the partial of f with respect to y of this right here? Well, the derivative of x squared z with respect to y is what? 0. Derivative of y squared x is 2ix or 2xy, same thing, right? And then what is the derivative of g with respect to y? It's the derivative of g with respect to y. So it's a partial derivative, right? This is a partial derivative of g with respect to y. But I need this right here to match exactly what I have up here, right? So I'll put but, or I'll say therefore, be a little more mathematical. Therefore, 2xy plus partial of g with respect to y must equal 2xy from above. What does that imply? That implies that the partial of g with respect to y must be what? 0. Do y'all agree with that? Partial of g with respect to y must be 0. Therefore, my partial of f with respect to y must equal just 2xy. Now what can I do here? Pardon me? Yeah, I know. We need to worry about that. This is what I said, right? This right here must be, so I've concluded that g, the partial g with respect to y must be 0, which of course meant that this right here is just 2xy. But what do I do with this? This is where we were kind of at the end of it last time, but now we still have to talk about the z component. So, oh, okay. G of yz, yeah, that means that there's, well, it could be just a z or a constant, right? That's the kicker here. That's the clue. That's the key here. So I want to know what this is, right? I mean, I really want to know what this is. What I know is its derivative is 0. So what I can do is look at this piece right here. Yes. It can't have a z attached to a y, right? It could have a z by itself though, and that's exactly what I'm going to say right now. The fact that g, the partial g with respect to y is 0, if I integrate both sides of that, right? If I integrate both sides, that tells me that g must be what? The antiderivative of 0 is just a constant, but again, because of what g is, since g is a function of both y and z, that constant could possibly be just a function of z. So here's the way I'm going to write it. It could be just a function of z, right? G could be, but it can't have y's in it anymore. So g is exactly some function of z. Make sense? So now what I'll do is I'll rewrite this again. I know that my f is equal to x squared y plus y squared x plus g of yz, which I just determined right here, must be some function of just z. And now I'm going to go and try and do the same game I've just been playing. I'm going to try and take the derivative again, this time with respect to z, and try and match it up with this piece. So if I take the partial derivative of f with respect to z this time, I should get x squared. That's the derivative of this piece. Derivative of y squared x is 0. What's the derivative of h with respect to z? Well, I can say h sub z. Even though it's just your standard derivative because it's a function of one variable, I'm still going to put partial of h with respect to z, because that still means a derivative of h, treating z as your variable. What do I need that to match? I need x squared plus partial of h with respect to z to match what I have up here, which is what? X squared plus 3z squared. So I need that to be equal to x squared plus 3z squared, which implies that the partial of h with respect to z must be what? 3z squared. Are you going to be able to now tell me what h of z is? This is the partial, right? So this is the derivative of h with respect to z, right? So what is h of z? Integrate both sides. Z cubed plus, this time it could be a constant, right? But this constant is not a function of x, y, or z. It is truly just a constant. So now I know what this h is, which means I do know f exactly now, well, within a constant. So f should be what is it? X squared z plus, what is it? X squared z plus y squared x plus z cubed plus a constant. That's what I believe my potential function is. How could I check it to see if it's correct? Just compute the gradient. Do the gradient real quick. The gradient is a vector. The first component is the partial of this with respect to x, which would be 2xz, right, plus y squared. Partial with respect to y, which would be 2yx, or 2xy. The partial with respect to z, which would be x squared plus 3z squared. And then the derivative of this constant is 0, so that doesn't matter, right? Does that match our f over here? Yes. All right. Questions? So if you're given a vector field and you're asked to show it's conservative at this point, you would need to be able to do partial integration to find a little f. Are you guaranteed it's going to happen? No. You're not guaranteed. So not the next section, but the one after that. In 2 sections from now, we will actually show what conditions we need in order to determine a vector field is conservative in 3-dimensional space. In 2D, we had a formula, and it was easy to check. But in 3-dimensional, we have to use something else. Okay, the homework for this section is here. But that's not the right page, so this is page 780 is where this starts. And you should probably only do 3 through 17, 780. Where that starts. All right, we've made it to Green's theorem now. This is a rather nice theorem. So nice, in fact, that they have an entire section for just this theorem. Okay, Green's theorem is a theorem that connects the line integral around a simple closed curve to the double integral over the region bounded by the curve. So first we need to establish what's called positive orientation. All right, if you have a simple closed curve C, right? Closed curve means that its initial and terminal points are the same, starting and ending points are the same. So if I move along this curve C, let's say I start right here, I move around, and I come back to that point. If I move around in the counterclockwise direction, then that's called positive orientation. Another way of thinking of positive orientation is that if this was a plane and you were standing on the plane and you were walking around the plane like this, that the region that you enclose, D, is always to the left of you. All right? So as I'm walking around, the region is always to my left. So notice that if you do have a simple closed curve C, you should always enclose some region, shouldn't you? Some region D. So we can call C the curve and D the region that it encloses. All right, here is what Green's theorem says. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane. Okay, positively oriented, counterclockwise, piecewise smooth, meaning that you can have little jagged parts of the curve, but you have sections that are smooth. So you could break it, like if it was jagged, you could break each little jagged part off into its own little smooth piece. That would be a simple, well, positively oriented. I would have to give you direction here, the arrows, right? Piecewise smooth. So I'm not smooth here because I have like this cuspy pointy thing, but I'm smooth in this piece, right? Smooth in this piece. So I would have four pieces, four smooth pieces. So piecewise smooth, simple, closed, right? Simple meaning it's not going to traverse itself. It's not going to cross over itself in the plane, which means we're two-dimensional. And let D be the region bounded by C. So D is the interior of that. If P and Q have continuous partial derivatives on an open region that contains D. So this is vitally important that we understand this part. P and Q are scalar functions. If the scalar functions have continuous partial derivatives on an open region that contains D, so on an open region contains D means that within the region, your derivatives exist. All right? If you have a discontinuity in there, then this theorem is going to fail. All right? Just, we got to keep that in mind because if I have time for it later, I want to show you something. So if all those conditions are satisfied, then the line integral, and then this symbol, let me explain this here. This symbol indicates, anytime you have an integral symbol and you have a circle here in the middle, you're telling everyone you're integrating over a closed curve, right? It's closed. And it's positively oriented, meaning that you're going counterclockwise. If for some reason you need to change the path's orientation, you need to go clockwise instead, that would be referred to as negative orientation, and you have to let someone know that you're going the other direction. So what you do is you draw the integral sign, but you draw a little arrow. So that means you're going positive. That means you're going negative. So without anything, everyone understands it's going counterclockwise. With this arrow on it, then you know it's going clockwise. Negative orientation. All right? So the definition here, or the Green's theorem says, if you are doing a line integral over a closed curve C with positive orientation of P dx plus Q dy, we talked about this before. I'm going to bring it up here in a second because I said, remember, like, we're going to need this notation later. Today's later. This integral, this line integral, is equivalent to the double integral over the region D of the partial of Q with respect to X minus partial P with respect to Y with respect to area. So you're able, with Green's theorem, to take a line integral around a curve and convert it to a double integral on the inside of it. All right? That's going to turn out to be good sometimes and bad sometimes. We'll see. Let me get back to this notation real quick. I want to show you that from 13.2. Go all the way to the back. This is where we were defining a line integral over a vector field, okay? And then towards the end of this, right here, I said suppose your vector field can be written as PQR, where PQ and R are the components of the vector field. Then this line integral over the vector field is equivalent to the line integral over the scalar function P with respect to X plus Q with respect to Y plus R with respect to Z. If we cut out the R component and make this a two-dimensional vector field, then this formula becomes P dx Q dy, right? That's it. So what I'm trying to get you to see is that this right here could be replaced with a line integral over a vector field. So we can actually do line integrals over vector fields and convert them into double integrals over a region, but two-dimensional only. Now there is an extension of Green's theorem, which we'll get to at the end of this chapter, where you can go to three-dimensional. But for now, we're in 2D, all right? All right, so Green's theorem. I would like us to look at this, evaluating the line integral over C, closed integral, closed curve, positive orientation, y dx minus x dy, where C is the unit circle centered at the origin. All right, so I've already told you positive orientation, haven't I? Because I've told you from the integral symbol that I want you to go positive orientation. Now, that's important because that means you need to draw the curve. When you do your parametric equations, you need to do it so that you draw it in a positive orientation. So as t starts, you go around counterclockwise. Now, I want us to do this two ways, using a line integral, so using the stuff from the previous section, and then using Green's theorem, and let's see which one is better, because one's probably going to be better than the other. So the first thing I need to do is maybe take a look at what we're trying to evaluate here. If I look at this here, I have a P and I have a Q. What are the P and the Q? P here for me is Y and Q is just X, right? Yeah. Now, to use Green's theorem, I have to let C be positively oriented piecewise, blah, 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 blah. P and Q have continuous partial derivatives on an open region that contains D. That means I need these to have good derivatives. And I need them to be defined on the region that I'm enclosing. So I'm going to draw a quick picture. The region that I'm enclosing is the unit circle centered at the origin. Right? Unit circle centered at the origin, like this. So if I'm anywhere on this unit circle on the outside or anywhere inside, are P and Q well defined? Yes? We're not going to get like division by 0 or anything crazy like that, right? So these are very nice functions. So I don't have to really worry about it in this problem. In another problem, I might have to worry about it. So I'm just checking those conditions are okay. Looks like my P and Q are nice on the circle and inside. So I should be able to apply Green's theorem. So for part A, was it part A or part 1? Part A. Let's do this using line integrals. Using line integral, the way that we do a line integral is we find parametric representations of our curve C. So can somebody tell me what the parametric representation of the curve C is? Cosine t sine t? Right? That's what we get. And then what's our restriction on t? 0, 2 pi. That should draw me C, shouldn't it? That should draw the curve C. So C is the curve that is defined by these parametric equations with those restrictions on the parameter. So this line integral up here becomes two integrals, right? The first one, I go from 0 to 2 pi. I need to put in y, right? What's y for us? Sine t times dx. What's dx for us? Well, it's the derivative of the x, so negative sine t dt. Then I'm going to say, what? Right here, I need to do what? Minus, because that's what it's asking me to do, minus integral from 0 to 2 pi, this time what? The x, which for us is cosine t, times the derivative of y, which for us is cosine t again, dt. Now I can turn this all into one integral. I can also factor a negative out. I'm doing that because I'm seeing that I have sine squared t plus cosine squared t. Do you see that? Right? I've got a negative sine squared. I've got minus cosine squared. These are the same integrals with respect to the same variable, so I can just turn it into one integral. This is just negative integral 0 to 2 pi of just, oh, I forgot my dt in there. There we go. Of 1 dt. That's t evaluated from 0 to 2 pi, negative t. So negative 2 pi. Everyone got that? Negative came out. Negative's here. Antiderivative 1 is t. Here's my negative in front. Plug in 2 pi, plug in 0, you get negative 2 pi. Was that terribly bad? That's pretty clean, right? I mean, not too much going on there. Now let's try it using Green's theorem. So for Green's theorem, part B, what I need to do is I need to take this p dx minus q dy, right? That's the formula for Green's. Plus, right? It's plus. So what am I going to need to do here? Because Green's theorem has a plus here. I'm going to have to look at this as plus negative q dy, right? That's the way I could use it for Green's theorem. According to Green's theorem, this should turn into the double integral over d of the partial of q with respect to x minus the partial of p with respect to y, dA. Well, what's p for me? P we said was what? X? Or Y? What was it? What was P for me? P was Y. And what was Q? So we need to be a little careful with this, because remember, we need this, for Green's theorem, we need this to be P dx plus Q dy. So for me, my Q, I know I set up here Q is X, but because of the minus sign, it should actually be what? Negative X? Okay. Change it up here and we'll change it down there. Do y'all follow that? Yay? All right. So I just need to take some partials here real quick. What's the partial of Q? I'm going to follow the formula here. What is it? I'm go double integral over d. What's the partial of Q with respect to X? Partial of Q with respect to X? Negative 1. Minus, what's the partial of P with respect to Y? 1. dA. Do you agree? That's just the double integral, right, of negative 2 dA over d, sorry. Can I pull out a negative 2 and have double integral over d of 1 dA? What is the double integral of 1? The area of d, isn't it? When you double integrate 1, it was that special case where really this just represented the area of d. Do you know the area of d? What's your region d? It's the part in here, right? It's all this in here, d. That's the unit circle. What's the area of the unit circle? Well, pi r squared, so it's just pi without any computation at all, right? So this is just negative 2 pi, which matches up the other one, doesn't it? So which one do you think was easier? Probably Green's theorem, right? Once you establish what P and Q are, this integral became very nice because you didn't actually have to compute an integral. Now, how would you have computed that had that not turned out to be 1? You would have had to have found some representation of D as a double integral. So you would have to probably look at this and say, this is a polar region. So you'd use a double integral in polar coordinates. Don't worry, we'll have an opportunity to practice that on the next example. Okay, so this was just to illustrate how a problem that was, it was slightly, it wasn't too bad, became almost trivial with Green's theorem. Let's look at our next example. Evaluate 3y minus e to the sine x dx plus 7x plus square root of y to the fourth plus 1 dy, where c is the circle centered at the origin, radius 3, right? So what if we wanted that? And let's do it both ways, line integrals and Green's theorem. All right, let me draw my region real quick. My curve is the outside, right? X squared plus y squared equals 9. So for part A, I've got to find a parametric representation of this curve. And I want it positively oriented. So C would be defined, X is 3 cosine t, Y is 3 sine t. T is between 0 and 2 pi. Is that all right? Yes. Well, it can be the right now we're trying to use Green's theorem in terms of the way it's written, but I said our left-hand side, our line integral, can represent the line integral over a vector field, which we've said can be like work or something like that. It just will depend on what we want to tie it to. Geometrically, though, it's the sum of two areas when we were looking at those, we talked about this before. You look at it from one perspective, and you look at what the area looks like. It's like, yeah, so it's like work, exactly. We don't have it right now because we're not looking at this as a vector field yet, but we can. And we will. I think on one of the next examples I'll do it. All right, so, man, do you see what a mess this is going to be? Because I can turn this line integral into the integral from 0 to pi, 0 to pi, and then I need to do 3y minus e to the sine x. So that's going to be 3 times y, but y is 3 sine t, minus e to the sine of what? 3 cosine t? Are you kidding me? All of that dx. What's dx? What's dx? Minus 3 sine t dt. That's just this first one, right? Then I have to do plus this one. Plus integral 0 to 2 pi. And then 7x, so 7 times 3 cosine t, plus the square root of y to the 4th power, 81 sine to the 4th t, minus 1. Oh, no, plus 1. And then all that dy, what's dy? 3 cosine t dt. Do you see this disaster? Anybody feel like integrating that? No? I don't even think I would want to put that in Wolfram alpha. I'm afraid of what it would say back to me, right? I think this is a pretty clear indication that maybe the line integral is not best done using this method. Maybe Green's theorem is better here, right? So I'm just going to put at the end of this, no. Like, I don't want to do that, right? Like, nobody wants to mess with that. So let's go ahead and try the other method. So let's see how nice Green's theorem is going to work for us here. If we are going to use Green's theorem, I need to define what P and Q are. So P would be this piece right here, right? That would be 3y minus e to the sine x. 3y minus e to the sine x. And Q would be, well, notice there's a plus sign on this problem, right? There was a plus. And in the Green's theorem, it's a plus in there. So I don't have to change the sign here. So my Q would be 7x plus the square root of y to the 4th plus 1. Now, are these nice continuous functions on that D region that I'm talking about? Well, I mean, look, do you ever have anything crazy happening here? I mean, sine's always defined, right? E to anything is defined. This is all good. How about over here? Oh, square root can't have a negative number, but y to the 4th plus 1 is always positive. That's never going to be negative. So you have no issues to worry about here, right? Everything is good. So we should just be able to apply Green's theorem to this. The line integral, right? My line integral of all that crap up there is equivalent to the double integral over D of the, what? Partial of Q with respect to X. What's the partial of Q with respect to X? 7 minus the partial of P with respect to Y. 3 dA, which is just 4 double integral over D of 1 dA, which is the area of D times 4, isn't it? Do you know the area of D? Pi r squared, right? Radius here was 3. So the area of that should be pi times 9 9 pi, but then times 4 out here. So your answer is what? 36 pi. Now, wasn't that nice? Wasn't that a lot better than trying to integrate all that crap up there? Questions? If you're able to do it, it should be 36 pi. Yeah, maybe Wolfram Alpha would be able to handle that. Yeah, we'll keep going. All right, so we can see that sometimes computing the line integral over a closed curve is easier when we use Green's theorem and convert the problem to a double integral. There are other cases when we would convert a double integral over to a line integral. Right? Maybe we have a double integral that we really don't want to do. Can we then convert it to a line integral instead? So here's an example. Well, I have to establish some stuff first. Recall from double integrals that the area of a region D is given by this formula, right? We just used that twice, didn't we? Area of the region D is equal to double integral over D of 1 dA. So if our Green's theorem, the part inside in Green's theorem, the part inside the double integral is partial Q with respect to X minus partial P with respect to Y, right? That's the part that's inside Green's theorem. This part. So what I'm saying here is the area formula will happen exactly when partial of Q with respect to X minus partial P with respect to Y is 1. Do you all agree with that? If this right here is 1, then you basically get this area formula, right? So what would P and Q have to be so that when you did the partials you got 1? So here's one option. If I let P be 0 and Q be X, then when I do my partials, don't I get 1? Look, if I define P to be 0 and Q to be X, then if I take the partial Q with respect to X, I get 1, minus the partial P with respect to Y would be 0, and so this would be 1. Do you all agree? Now, why do I care about that? Because that means that the area, right, the area formula of this double integral converts over to a line integral over C of what? I don't have the formula written there. It's the line integral C. It was what? P dx plus Q dy, right? That's Green's theorem right there. I'm saying for this right here inside here, if this is a 1, I could make that happen by letting my P be 0, my Q be X. Which means that when I go and I convert the double integral to a line integral, if the P is 0 and the Q is 1, or the Q is X, then this line integral just becomes line integral of X dy. Do y'all see that? So there's a new formula. Look, this is an important thing. If you want the area of the region D, you could do the double integral of 1, or instead, you could do the line integral of the curve around it of just X dy, and you'll get the same answer. Or what's another way I could have made this part inside Green's theorem 1? I could have done it this way. I could have let my P be negative Y and my Q be 0. So go over here and compute this. Partial of Q with respect to X would be 0, minus partial of P with respect to Y would be negative 1, minus the negative 1 is 1. So I would get the 1 inside the double integral if I did this, and it would convert the line integral into what part would die off? This part, the Q would die off, and then this part with the P would appear, which is how you get this. Are y'all following this? And then there's another way you could do it, and there's multiple ways, but this is another way. You could let P be negative 1/2 y and Q be 1/2 x, and when you did the partials, you would get 1, which means you could convert it into this formula. So what I've given you here are 1, 2, 3 different formulas for finding the area of a region D using line integrals as opposed to using this. Now, do you think that you would ever want to use it? How about this? Find the area of the figure below, an epicycloid, given the parametric equations. So if someone gives you the parametric equations for this curve, and they want you to find the area here, why is this not something you're going to want to tackle with a double integral? For double integrals, you need to be able to define the region, right? I need to be able to define this region. Is it a type 1 region? No, right? I mean, doesn't look type 1 to me. I mean, there's all sorts of things happening. You try and look over here, the top and the bottom are the same curve, and then up here it's all the same curve, right? It's all drawn by that set of parametric equations. It's not type 1, it's not type 2, it's not a polar region, right? I mean, you're running out of types here, right? Yeah, I mean, but I'm saying it's not one of our obvious, like, theta's between two constants, r's between two constants. You know, it's not one of our common things. So you could possibly attack this as a double integral. But why would you want to? I mean, why would you actually want to? You have the actual equation of the curve, don't you? I mean, you know how this curve is drawn. You have C. You're trying to find the area of D, but you have C. So why don't we use that in Green's theorem to try and come up with the area? Understand what I'm getting at here? Okay, so let's try and work this out. So we've got this epicycloid looking thing. We're given x is equal to 5 cosine t minus cosine 5t. We're given y is equal to 5 sine t minus sine 5t. We're given our restriction on t is 0 to 2 pi. I would like to know the area inside, right? That's what I want to know. We'll call that region in there D. I would like to know the area of D, which we all know, hopefully by now, that's the double integral over D of 1 dA. If we can define the region D in some coordinate system, we'd be able to do this double integral. But that's the challenge. We can't easily do that. But according to what I just put on the board, this is equivalent to 3 different line integrals. So which of those 3 equivalent line integrals would you like to use? How about we have this one, line integral closed positive orientation of what, x dy? Yes? We could use that one? What are you going to need in order to use this line integral? You're going to need to know the parametric representation of the curve, which you have. You need to know what x is. Here it is. You need to know what dy is. Do you know what dy is? Yes, it's right there, right? You'll be able to take this and multiply it times the derivative of that, and then you'll have to integrate, let's see, your c here, right? You're going to have to find limits of integration. But do you see that we could use this formula? I mean, it looks like this is very promising. I do have a couple of questions, though, before we apply Green's theorem. We have to make sure that, you know, our region is defined, you know, our parametric equations here are defined. I mean, there's no problems in here, right? Trig functions, they're well behaved, so we're good to go. Is it positively oriented? So when I draw this curve, is it, when I'm drawing it, is the region always to my left? Because that's also a requirement here. Should be. So how could we check? How about we start at 0 and see where we are? We start at 0, what point do we get? So if t is 0, what's cosine of 0 is 1, right? Cosine of 0, 1, so where are we? 5 minus 1 is 4, so we should have an x-coordinate of 4, and then a y-coordinate of, same thing, we go in, sine's going to give you 0, so you get 0. So we're right there, right? We're right at this point, okay? So now I need to know what happens if I plug in something bigger. So how about a value we know? How about pi over 2? Okay, what am I hoping for? Where I'm hoping to be up here or down here? Up there, right? That's what I'm hoping for, because that would be positive orientation, counterclockwise. So what happens if I plug in pi over 2? X would be cosine of pi over 2 is 0. Cosine of 5 pi over 2 is also 0. So you get 0. So x-coordinate 0. The y-coordinate, sine of pi over 2 is 1. Sine of 5 pi over 2 is also 1. So you get 4, which does put you up here. So I'm convinced, okay, without going into more detail, I'm convinced that it is drawing this thing counterclockwise. So I am comfortable with this being positive orientation. What if it was the other way? What if it was drawing it the other way? What could I do? I would write that as, I would be integrating over negative, right? I would want to change the orientation of C, so I'd make it negative. And what happens when you change the orientation of C on a line integral of x with respect to y? Does it change the sign of the integral? Yes. That was back in our notes. When does it not change the sign of the integral? When it's with respect to what? ds. When we went with respect to arc length. But when you go with respect to y, it does change the sign. So all that would happen if it was drawing it the other way is that we would just change the orientation to make it positive, and just we would throw a negative out here. All right? Okay. But we're lucky. It's not. So what I need to do now is just rewrite this line integral. I have limits of integration from 0 to 2 pi. My x was 5 cosine t minus cosine 5t. Right? And then I need dy. So what's dy for us? 5 cosine t minus 5 cosine 5t. dt. Do y'all agree? And now I'm going to actually just multiply this all out. 0, 2 pi. Let's see. 25 cosine squared t. And then what do we have here? That's this and this. Now here to here. Negative 25 cosine t cosine 5t. What about the middle one? Minus 5 cosine t cosine 5t. And then the outer one, the last one there, plus 5 cosine squared 5t. All of that dt. These two in the middle can go together, right? And you might be saying to yourself, well, that looks kind of ugly, right? But I would argue that that's a lot better than you trying to come up with some sort of representation of D. I mean, this is a Cal 2 problem right here, right? I mean, power reducing formula here, power reducing formula here. These two, I probably use a product to sum formula, like a product to sum formula from pre-cal, like how we turn products into sums. You could break this into two separate trig functions and then integrate each one by one. I just covered that in my pre-cal class today, so I know it is taught, right? How do you do cosine, cosine? I wonder if it's in your formula sheets. They don't have them here on this one. But it's doable, right? That's doable. So I'm not going to take it the rest of the way. You understand what you would have to do, though, right? Now, I just wonder, if we did it with, remember I said there was different formulas, like we could have used this one, or we could have used like, line integral, negative y dx? Do you think that that would have made any difference in the complication here? You don't think so? We should have something similar to this. Is it worth looking at? Or no? I mean, do you want to? It doesn't. Maybe we just look at the beginning of it. What would the integral look like if we had done? Instead, we had done line integral c. We did negative y dx instead. Negative y for us would have been what changed the y, so it would be negative 5 sine t plus sine 5t. That's y, and then derivative of x would have been negative 5 sine t, then plus 5 sine 5t dt. Is that any better? I mean, it's looking like we're going to get what here? About the same thing, right? This and this. Do y'all follow? This and this. Doesn't look any better, does it? How about that third option? We had a third option, didn't we? It was what? I could do negative 1/2 y dx plus 1/2 x dy. I could do that one, right? Couldn't I do this? That's what I said. That was an equivalent form also. Would that make it any better? You don't think so? Think about this. If we multiply, okay, let me multiply this one out up here. We would have got 25 sine squared t. It would be minus 1, so minus 30 sine 5t, or sine t, sine 5t. Come on, damn it. And then it would have been, my last one would have been plus 5 sine squared 5t. Y'all agree with that? If I would have done this foiled out, collect like terms, negative, negative, okay, positive. That's what I would have, right? That's negative y dx. So I'm supposed to take negative y dx and take half of that. Just half all of these right now. So I'll write that down. Half of all of those. 25 halves sine squared t minus 15 sine t sine 5t plus 5 halves sine squared 5t. All right? That's this part. I'm supposed to add to that what? Half of x dy, which was the previous part of this thing, right? So let me add to that, and I'm going to do it below. Well, I'll squeeze it in. Add to that the previous page, which was 25 cosine squared t minus 30, right? This. Here we go. Help me out. This will be 25 halves cosine squared t minus 15 cosine t cosine 5t, and then plus 5 halves, thank you, cosine squared 5t. Now, does this one look good? Check this out. What's 25 halves sine squared t plus 25 halves cosine squared t? That's just 25 halves. I still have the integral, okay? Integral. It's actually 0 to 2 pi. 0 to 2 pi. And there's a dt at the end of all that, okay? I'm out of room. But that's just 25 halves. Hell yeah. And then, what about 5 halves sine squared 5t and 5 halves cosine squared 5t? That's just 5 halves, right? And then, what about this? This and this. Can I do anything with that? Dun 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 dun. I just pull out negative 15. That all right? All of that dt. Anybody recognize this? Do you remember the formula for what's sine of u plus v? That's sine u cosine v plus cosine u sine v. Remember that? That's the sum formula for sine. Do you remember the one for cosine? What's cosine of u plus v? It's what? Cosine u cosine v? Are you looking off your sheet? You have a sheet? Good. And everyone else have their pre-cal sheet somewhere buried? So what's cosine u plus cosine v? I mean cosine of u plus v? Cosine u cosine v minus sine u sine v. I don't have a minus between, I have a plus, right? So on the formula sheet, if you change this to minus, right, it changes this to a plus. Yes? So then this order doesn't matter, does it? So this, are you telling me that this thing turns out to just be what? Negative 15 cosine. Does it matter if I say t minus 5t or 5t minus t? Does it matter? Because it's cosine, it's an even function. So if I put in here t minus 5t, I would get what? Negative 4t. If I put in 5t minus t, I get 4t. But cosine of u is equal to cosine negative u, so this isn't going to matter. Here's where I am, 0 to 2 pi. What's this? 30 halves, is that just 15? Those two? Minus 15 cosine 4t. Can you integrate that? What's the moral of the story here? That's why they give you three different forms, because sometimes one of them is going to be a lot better than the others. It just depends. In this case, it was great. This third format was great because a lot of my signed trig functions trig identities were able to come into play. I'm going to go ahead and finish this out. What's the antiderivative here? 15t minus or plus 15 fourths sine 4t evaluated 0 to 2 pi. Yeah, it should be minus, right? It's not going to matter, is it? This part's not going to matter? Because now plug in 2 pi. You get 0 for the sine part, right? So 30 pi is the answer. 30 pi. Wow. I wonder if this problem's in the book. I don't remember where I got this problem from. Epicycloid, yep. Let me see if this is in here. It's got to be. I usually try and pull problems that are in the book somewhere. Huh. Well, I would love to verify that that's the correct answer because I went through that so quickly. But it looks good to me. I mean, I don't see any issues we ran into, right? And all this trig stuff seemed pretty clean. So, okay. I hope that I've made my point, I guess, that this is Green's theorem is useful. You can use it to find areas backwards. You can use it to find line integrals by just being able to define that region it encloses. Now, Green's theorem, here's another version. Okay, just remember I said that you could rewrite this, which is basically your formula for work. You can use Green's theorem here because what we do is we rewrite the capital F, the vector field, as a P and a Q, right? So we have P and Q here. All right, so let's try and get our heads around this. We want to find the line integral on the vector field over C, over the vector field on C. Here's our vector field, and we're going to integrate over this triangle. Okay, so let me draw the triangle. Okay, here's what we've got. The triangle goes from 0, 0 to 2, 6. To 2, 0, back to 0, 0. So I've given a direction, haven't I? That's my curve C. Somebody tell me what I should do first. And I want you to think about this big picture here, okay? Like, what should I be doing first? I'm being asked to find the line integral over a vector field on this curve. What's the first thing that pops into your mind? Mr. Acuna is here. Yes? No? Joel? No, Jose. Jose, right? Okay, Jose is here. Aguilar. Diego's here. Jason, Adrian. Joshua's here. Jose Riojas here, right? Okay. Tamara's here. Patrick's here. Ali's here. Diego. What am I missing here? Raul? Right? Okay. I've got everyone. 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. It's not positively oriented, right? Do you all agree with that? Okay. Good. So we would, if we're going to use Green's theorem, if you're going to do it, you're going to need to orient it positive. What else? There's something even more fundamental, even further back, that I would want you to think about here. Because we're in the Green's theorem section, I understand that, but it would never be presented this way. Like, use Green's theorem, it would never be presented that way. So why don't, you would be looking at it from kind of a different perspective. We'd have to find the curves. So that would be, you would have to find parametric representations of 3 line segments, right? You have to find, okay, what draws this? What draws this? What draws that? Okay? Even further back. Kind of. Let me see. Maybe this will help. What was the section before this? What did this say? That if your vector field is the gradient of something, right, then this is just the little f evaluated at the endpoints, right? If I'm on a closed curve, the starting point and the end point are the same, which means that the answer would be 0, wouldn't it? If my vector field is conservative, right? So if I'm presented a problem like this, the first thing I'm saying to myself is F conservative? Because if it is, the answer is 0. Because I'm going over a closed curve, starting and end point are the same. So when I plug in the 2 endpoints, and I wouldn't even need to know what little f is, because I know that it's going to be the same value beginning and end, so the answer would be 0. So if I were doing this problem, before I go start to just grind away at it, I would first ask myself if this is a conservative vector field. How do I check it if it is? Partial. So what is the partial check that we do? Do y'all remember it? Let me see. I'm trying to figure out where it was in the notes. It was in 13.2, I believe. Maybe it's not in 13.2. Partial Q with respect to Y. Where is it? Do you see it in your notes somewhere? Because I want to be able to refer to it. Oh, here it is. There it is. There. To check for a 2-dimensional vector field to see if it's conservative, you do partial P with respect to Y. Is that equal to partial Q with respect to X? Isn't that? Hold on. Hold on a second. Isn't that this? If these two are equal, what is this? 0. And what's a double integral of 0? 0. That's where the check comes from, basically. It's the fact that the line integral will be converted into Green's theorem. Green's theorem says if that's 0, then the line integral is 0. Conservative vector fields give you 0. So, I mean, on a closed curve. pretty awesome result there. I'm just trying to show you that this came from the idea from Green's theorem. I can't get over there, but you know what I'm saying. So that's the first thing I would check. That's the first thing I would check. Get this out of here. So what is the partial of P with respect to Y? Partial of P with respect to Y. 2y cosine x. What's the partial of Q with respect to x? Are they the same? I'll write it down. So I'm going to check real quick. I'm going to check, is F conservative? If it is, the answer is 0. So the partial P in this problem is y squared cosine x. Q in this problem is x squared plus 2y sine x. The partial of P with respect to y is equal to 2y cosine x. The partial of Q with respect to x is 2x plus 2y cosine x. Are they the same? No. Shit. All right, well, good check. At least I thought about it, right? Because I would hate to invest the next 20 minutes into a problem that I could have said is 0 from the very beginning, right? You would hate to do that yourself also, right, on a test? All right, so let's now just go through it. I realize I have this curve. I realize it's oriented the wrong direction, right? So I'll just make a note up here that negative c, right? Negative c goes this way. And I could go and try and find the parametric representation. I don't want to do that, though, because this is a closed curve. It's simple. It's connected. It's smooth, right? Piecewise smooth. I do have points, but piecewise, they're each nice. So it's a closed region. I can use Green's theorem as long as the functions are well defined there. And these functions behave very well, right? Trig functions, polynomials, they're all good. So I just need to somehow come up with a way of representing that region. Am I going to be able to represent this region in here, D? Absolutely. Type 1 region, right? It's a type 1 region. So let's write this down. I am going to take the line integral over C of f dot dr. I'm going to realize that that really means P dx plus Q dy, because we defined that way back in 13.2, that this was the same thing. And then I'm going to say, but because of Green's theorem, this is double integral over D of partial, right, partial Q with respect to x minus partial P with respect to y dA, so long as I can come up with this, right? As long as I can come up with some representation of D. But also, this C had to be positively oriented, right? This C had to be positively oriented. My C's not. So what I'm actually looking at in my problem is I'm going to be looking at, I mean, how do I change this to make up for it? This here is the same as, how do I need to change to adapt to the fact that the theorem only works if I'm positively oriented? I need to make this a negative C, right? So if this is negative C, it means the opposite orientation. This part is true, right? This is true, that the negative orientation of C should be equal to this. But these two are not the same, are they? Because I've changed it. So what do I need to do? I need to throw out here, what? Negative? Negative? Now it's the same, because remember, when we change the orientation, because of these two integrals, they change their sign too. So if I go from C to negative C, it's going to change the values of these two to be negative instead. And that means that the integral is going to be changed that sign also. It's a subtle thing. I mean, look, the worst you're going to be off by is a sign, right? I mean, it's not the end of the world, but you do need to account for it. Okay, so now let me just find this double integral. This is negative double integral over d. What is partial of q with respect to x minus partial of p with respect to y? It's partial q with respect to x was here, right? Partial of p with respect to y was here. So you got what? Just 2x dA. Yes? Now give me a way of representing this region. As a type 1, right, your x values went between where and where? 0 to 2. And your y values were actually functions of x, weren't they? The bottom y value was 0. And then the top was that line segment, which has a slope of what? 6 over 2, so a slope of 3. So that's just y equals 3x, isn't it? So this is 3x up here. So that means 3x here. So my double integral looks like this. Negative 0 to 2, 0 to 3x of 2x d what, d what? dy dx. Okay? And that's it. I won't take it the rest of the way, but you get the idea? All right, let's check this homework assignment. Oh, shoot. You know what? I think I'm going to come back to this and do this. This is not in your notes, right? I don't believe this is here. I'll do this next class if we have some time, all right? Because I need more than 14 minutes to explain this properly, but I think it's important enough to talk about, all right? So I will come back to that, time permitting. It's not the end of the world if you don't see it. It's just a really cool result. Yeah, so that was the example I'll do with that. So here's the homework, 787. That is the correct page. Those are the correct problems. Number 29 you can not do right now. Everything else is good. Now we have 15 minutes. I don't want to stop class because the next concept from the next section I can show you. It's quick. There's not a whole lot of new formulas. A lot of it's visual, so we can just get right to it. I'm trying to give us as much time as possible for the last 3 sections of this book because they're a little intense. Has it seemed like this class has gotten intense or not? I don't know. What do you think? Your perspective? It's new stuff, but not necessarily super complicated. I don't know. I mean, okay. It's extension of everything that you did in Cal 1 two-dimensional setting, really. Okay, so let me show you the code, not the code. Where are we at? 13.5. Make this nice and big here. Curl and divergence. So these are vector field operations. We're taking a step away from everything we've been doing for a second to define two operations. All right. So it's going to seem like whoa, wait, why are we talking about this? It's just because we'll need a little parts of it for where we go. But if it seems different, it's because it kind of is. All right. Given a vector field F. All right. So someone gives you a vector field. So remember, vector field. You've got at every point in the space, you've got a vector, right? At every point, there's a vector. It could be two-dimensional or three-dimensional. Do I need to show you a picture of a vector field again, or are we okay? Are we okay, or do you want to see a vector field? You're fine? Okay. All right. Now we're going to define two different operations on that vector field. The first one is the curl of F. When we take the curl of F, we're going to get a result that is a vector. Then we're going to get something called the divergence of F, which is going to result in a number. Two different operations. Almost like, remember if you had two vectors and you dotted them, you got a number, but when you did two vectors and you crossed them, you got a vector? Cross product two vectors is a vector, dot product two vectors is a number. Well, the curl of a vector field is a vector. The divergence of a vector field is a number. What do they mean? That's why I want to show you this, because when I first did this, well, this is the actual mechanical computation. We can come back to this next class. I don't want to get tied up in this. There's a formula for curl. What I want to show you is what it means, all right? So I spent a lot of time trying to come up with a visual representation of curl. And it usually brings my computer to its knees. Let's see how this works. This is one of the most difficult programs I've ever written in Mathematica. Okay, so you have a vector field. You have a vector field. At every point in the three-dimensional space, right? At every point, there's a vector. That's not what the curl is. But let me get the field out of there. What else do I want to do here? The computer here is computing the curl right now, okay? It's computing the curl. And you can see that the curl is a vector. So it's giving me a direction, right? The vector is a direction, but it's not the same direction as the vector field is, all right? The vector field is pointing in some direction, right? But then the curl is somewhere else. It's pointing somewhere else. And then if I take the magnitude of the curl, I get a number. So now what I'm going to do is I'm going to start playing this, all right? My point is not moving, all right? My point is staying there. Do you see that I have a red vector is like a little line segment, then I have this disk, and that disk is rotating now, all right? So what's happening is that imagine that these are like molecules, water, in some container, and there's moving around, right? If you are a single molecule right here, the vector field tells you which way you're pointing, right? Like which way you're headed, the vector field dictates that. But because of all of the things happening around you, you have some sort of rotation to you also. Okay, so I might be headed towards let's say the projector. I might be headed there, but because of the, let's say, water molecules around me, I might actually be like spinning at the same time as I'm heading that direction. The red part here is the curl vector. So maybe I'm headed towards the projector, but I'm spinning like on an axis of rotation like here. So I'm spinning like this as I head that direction. So the curl gives you the axis of rotation of your curling, and the magnitude of the curl gives you how fast you're rotating. So watch, if I move this, notice how it's rotating right now. It's pretty slow, right? My curl's 1.79. My magnitude of my curl. Let me pause it so I don't freak everything out. Let me move it to somewhere else where I have maybe would like to have a larger curl. 2.3 3. Okay, so now I'm going to have to rotate the whole thing so we can see it. Cut it off. Let's just play it. I might have gone outside the domain. You see how much faster this one is? There we go. Curl's 3.2, the magnitude of the curl. So that's a much faster rotation there, isn't it, than it was before? Compare that to another point somewhere else in here. I want to get smaller. There we go. 0.33. Look how slow that rotation is. You see? So as things are moving around, right, at an instant in time, that little molecule has a very, very small rotation happening, right, on that axis of rotation. So curl is a measurement of that. Got it? Understand it geometrically? So it can be a little overwhelming to understand it in 3D. So sometimes we do it in 2D instead. By the way, what made this one of the hardest programs for me to write is to try and get it to draw an arbitrary circle that was oriented anywhere in three-dimensional space. That was very difficult. That was a challenge. I mean, it's easy to take a circle and just move it left, right, up, down, flip it over, but to actually in three-dimensional space move it at any angle, and still, what's the equation of a circle, right? What's the equation of a circle if you change the angle in three-dimensional space? It's a lot more complicated than what's the equation of a circle if I move it up, down, left, right, flip it over. That was the hardest part. All the timing of everything came pretty naturally afterwards, but where are my computer science people? Do we have any computer science people in here? It always had to be, yeah, well, it's not arbitrary, but it always had to be parallel. The circle always had to be perpendicular to the curl vector, right? But that curl vector could be anywhere. So, like if I ask you for the equation of a circle on this plane, that's pretty easy, because one of your variables is 0. If I ask you for the equation plane on the ground, it's pretty simple because one of the variables is 0. Or on that wall, it's fine. But if I say draw a circle in this room so that there's a line pointing through right here, and just draw me a circle, what's the equation of that circle? Much more difficult than, because I can point that anywhere. That was the hardest part. Here's I mean, if you want, you can, mess with it yourself. See if you can come up with it. I wouldn't expect anyone in here to do it. Where is it? I don't even know where it is in here. Rotating black line and circle. I'm not sure where it is. It had to be built off the vector, correct. There it is. Here's the formula for the disk right here. It's been so long, I don't remember what I did. It's not important. We can talk. That's something we can talk about later. Let me get into a two-dimensional representation of curl. All right, instead of the 3D. Sometimes it just works out a little bit better. So for curl in two-dimensional space, the issue that you run into is this. For curl, you need a vector, right? And as we'll see, the computation of curl involves a cross product. But we've said that, you don't define cross products unless you have three-dimensional vectors. So what we do here is we imagine that there's a third component that comes straight out at us. All right, so remember that in the previous example I had the red line, the disk was going around it? Our red line is coming straight out of the page. So our red vector is always coming out at us. So what's happening is imagine a point, right? If I take a point right here, everywhere in this vector field it's going down, right? It's wanting to go down. But if I move out to the right, it wants to go down faster. Imagine that point has like little paddle wheels on the outside of it. then what would happen if I start moving this thing around? Why is this not playing? Oh, it is playing. My wheel's not rotating. Why? Why is it not rotating? It balances, right? Is that what you said? It balances. The force acting on this side of the paddle wheel and this side are the same. So the paddle's not moving. And if I move this thing, to the left, boy, something is up. Shit. Okay. I don't know why it's running so slow. That's a little too fast. Let me slow it down. Am I running this backwards? What's going on here? Okay, there we go. I must have hit the backwards. Does that make sense that our paddle wheel would be rotating that way? Because the ones out here are flowing faster than the ones here. So if you're like a little molecule, the ones over there are kind of rubbing you, going past you faster than the ones on this side. So you're spinning like this as you're going down. So there's your curl. Make sense? Now we can do this. We can do this for. See, we move it to the other side. What will happen? Should rotate the other way, right? I don't know why appears my paddle's going the wrong way, isn't it? I'm running time backwards right now. It's rotating this way, right? Does it make sense that it would rotate this way? Okay. All right, now what if I change my vector field? What if my vector field looks something like this? It's a little harder to tell what's going on here, right? But I can move it around. And notice here that no matter where I move it, my curl is always 0. You see that? Curl is always 0. I know it doesn't look like it would be, but it is. And if you don't believe it, we would just take the vector field and compute the curl. All right? That kind of makes sense? So the curl vector creates an axis of rotation. The magnitude of the curl gives us the speed of the rotation about that point. If the vector field represents the velocity, oh wow, I'm out of time. Blah, 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 blah. We'll get back to this. If curl is 0, it's irrotational. But here's the main result. Suppose F is a vector field in three-dimensional space. If the curl is 0, it's conservative. That's where the idea of a conservative vector field comes from. The curl is 0, meaning that at every point, there's no rotation. So things are moving, but they're moving in a way that there's no rotation at all to like an infinitesimal point. All right? That's what conservative vector fields do. That's how they behave. All right, well, that's it for the week, right? Yeah, we're done. So you have enough homework. You have your take-home quiz, right, that I emailed out. That's due, last day of class, right? Or I think it was set to be due the last day of class. You can check. Right? Is that not what I said? I'm pretty sure I said it for the last day of class. The 3rd, that is the last day of class. Well, before the final. So it's the last day that we meet here for lecture day, and then we have the finals the week after. So we only meet, 4 times? 4 more times. That's it. And then we have a final. Don't cry. You'll be okay. All right, y'all have a good day, okay?